Okay, physics friends, today we're going to look at a problem that involves two objects connected by a string. And these are problems that sometimes we refer to them as two-body problems or multi-body problems or system problems. And they can be a little challenging at first, but once you get it down, the methodology, it's really quite easy to solve. So I'm going to walk you through that process today. Okay, so I have two boxes. Mass 1 is 10 kilograms and it's hanging. It's looped over a frictionless, massless ideal pulley. And mass 2 is sitting on a rough surface and it has a mass of 15 kilograms with a force of friction that acts on it of 72 newtons when these boxes are in motion. Okay. We're going to assume that the string is also ideal. And what that tells me is that if there's one string, there's one tension everywhere within that string. If a problem was to tell you that the string had mass, or the mass was large, or that it varied, then you cannot assume that the tension is the same everywhere in the string. But for this case, we can. Okay, two things I'm going to show you how to do today for problems like this. The first is what is the acceleration of both objects, and the second is what is the tension in the string. So I can claim that the acceleration for both objects is the same, and that is true because they are connected by a string. They will move with the same acceleration. So let's start there. The first thing I need to do is make a free body diagram. Because this is a force problem, and I like to number my objects. So I always start with a hanging object, and I'm going to call this one number 1, and I'm going to call the object up on the table number 2. It helps me keep track of similar forces. So for example, the force of gravity acts downward here on object 1, so I'm going to call that FG1 because I'm talking about object 1. But gravity also works on this object here on the table. So I'm going to call this one, instead of just calling it FG and getting it confused, I'm going to call this FG2 because that's object number 2. Okay. The next force that I have to look at, well, what is the other force acting on object 1? That would be tension. And tension always works away from the object, points away from the object. Remember, tension is like a pulling force. It's never a pushing force. So this is the tension here in the string. And then up here on the block on the table, it's also being pulled by the string. So tension goes this way. And these two tensions are the same. Remember, it's one ideal string, so the tension at one end is the same as the tension on the other. So I'm going to call this T and T. And two more forces. Over here on the tabletop, because my box is sitting on a surface, that means that I have a normal force, Fn. And then because the box is going to be accelerating to the right, that frictional force of 72 newtons, that's going to act opposite that direction, or it's going to work towards the left, the force of friction. Okay. All right, excellent. Now we're ready to start. All right, so with a system problem, the next step you should do is write a net force equation for each object. Then we're going to combine them into one equation for the system. Okay. So starting with object number 1, my F-net equation, so that would be F-net, remember, that's the helping forces minus the hindering forces. Okay? So let's just think of forces in terms of helping and hindering. So for object 1, which is moving down, this is the direction of motion, what's the helping force? The helping force will always point in the direction of motion. So for object 1, my helping force is Fg1. And the hindering force is always going to point opposite the direction of motion. So that means minus tension. Okay. Object number 2 on the tabletop, well, this object isn't moving up and down. It's moving, or it would move, to the right. So what's my helping force here? pointed in the direction of motion, my helping force is the tension. And my hindering force points opposite the direction of motion, so that would be the force of friction, minus the force of friction. Now I like to draw a line right underneath these here and add them up. And well, when I look at this, I see a minus tension and I see a positive tension. And if they're the same value of tension, then positive T and minus T, they're just going to cancel out of my equation. And so then I'm left with Fg1 minus the force of friction. And this is for the system. This is the system net force equation. So I'm going to set this equal to the mass of the system times the acceleration. And the mass here is important. It has to be the system mass. It has to be everything that has mass. Otherwise, you're not talking about the system. You're talking about an individual object. Okay? All right, so here we go. Let's solve for A. Well, how do I find Fg? Well, remember that Fg is equal to mass times the acceleration of gravity. And so Fg in this case is going to be m1 times g, and my force of friction here is 72 newtons. And then my mass of the system, well, that's the sum of all the masses. Well, I have m1 plus m2 times the acceleration. So now I can plug some numbers in here. So this is going to be 10 times 9.8 minus 72 is equal to 10 plus 15 times A. So this is 98 minus 72 is equal to 25A. And 98 minus 72 is 26 equals 25A. And divide by 25. That leaves me with an acceleration of 1.04 meters per second squared. And that's our acceleration for the system. So that qualifies as the acceleration for both mass 1 and mass 2. All right, so let's talk about how we can find the tension, because this is a little different. Okay? So the tension is going to be the same, remember, on both of these ends, because it's an ideal string, one tension. Well, could I use the system equation to find tension? No. Why can I not? Because there's no tension in this equation. It's just Fg minus friction. What equations have tension in them? These two have tension. And they're both valid F-net equations. They're just equations for individual objects. That's easy enough. So let's pick the one that's easier. Well, in this case, they're both relatively the same. Sometimes you'll get one that's just tension equals ma, and that's nice easy. Okay? So I'm just going to use object number 1 for this case. Okay? And I rewrite the individual net force equation. So for object 1, it's Fg1 minus tension, and now I'm going to set it equal to ma. This mass, though, is no longer the system mass, because I'm only talking about object 1. So this mass is 10. So let's plug in what I have. Fg1, that's going to be m1 times g minus tension. This is going to equal m1 times a. So this is 10 times 9.8 minus tension equals 10. And now the acceleration, I'm going to get that from here. That's the system acceleration times 1.04. Okay? So 10 times 1.04, that leaves me with 10.4, and that equals minus t and 98. Okay? So I'm going to add t to the other side and subtract 10.4. So I get 98 minus 10.4 is equal to tension. And so that gives me a tension of 87.6 newtons. Now you could also plug that in here with the force of friction and make sure that you get the same acceleration to check yourself. Or you could plug MA here and use the 15 kilograms and solve for tension that way. But you should end up with the same answer. Okay. So this method, this system method, where you have the individual equations and then you combine them to get the system equation, that will work for a system that has 2 objects, 3 objects, 4 objects, lots of different objects. So don't be afraid, just draw your free body diagram and write out those net force equations. Have fun!